Ja, jullie, ga lekker zitten. Nou, welkom allemaal bij wat dan weer de 11e overgang. Super dat jullie er al zijn. Sommige nieuwe, sommige mensen hebben het al vaker gezien. Net lekker gegeten, ik hoop dat je een lekker biertje hebt gehad. En niet te veel, want je mag anders straks nog een rondje rijden in de placeseat. Voor wie dat wil, die kan een rondje Zandvoort of een dagje Zandvoort zelfs winnen. Dus neem straks nog even plaats en rij een rondje. Maar eerst gaan we, eigenlijk omdat we bij internet jongens vind ik wel belangrijk dat we steeds iedere dag alles net weer een beetje beter doen dan de dag daarvoor. En daarom proberen we af en toe eens een interessante spreker uit te nodigen, zodat we daar nog wat van kunnen leren. En ik denk namelijk dat het ook echt zo is, want net even met Arnout staan praten. Ik ben zelf niet zo'n programmeur. Maar wat ik van jouw talk begrijp is dat we er echt wel iets aan hebben. Omdat volgens mij heeft iedereen met data te maken die je uit een systeem haalt en die je ergens op een bepaalde manier toont. En is het voor iedereen interessant om dat dan ook op een goede manier aan de eindgebruiker te representeren. Maar daar ga jij alles over vertellen. Dus ik zou zeggen, pak een biertje.
Alright. So I'm gonna do this talk in English because yes, there are English-speaking people. Yes, I'm not doing it in English for no reason. Very nice. All right. So this talk is titled of Representation and Interpretation, and what I want to talk about this evening is I want to talk about hard problems in programming. And there's a classic joke that there are two such problems, right? There's cache invalidation, there's naming things, and there's off-by-one errors. But I notice a lot of more problems that people often struggle with. And those are things like string escaping for HTML or for SQL or something like that. Time zones are something that we often mess up. Character encoding is often something we struggle with. And what I noticed is that a lot of difficulties with these topics are related. They are all related to how we handle and present data. So in this talk, I'm going to talk about this and how we handle data. You should know that this talk is a bit of a personal view. It's not an absolute truth or something. I'm just going to talk about how I look at these topics, and I hope to make you think about this for yourself and develop an own view on it. So let's start with, well, the central piece of this talk, data and what it means. Let's show some examples of data. For instance, we have a number here. Which number does this represent? Any takers? I already heard 3. Very nice. It could be 11 if we interpret this as decimal. It could be 3 if we interpret this as binary. It could also be hexadecimal. In that case, this would mean 17. So this number is meaningless without our interpretation of it. Let's look at some other data. We could find a byte somewhere in memory of our system, right? We put a 0x in front of it. Now we know it's hexadecimal because we usually write 0x in front of that. But, well, what does this byte mean, right? If it's a number, it would be 66, but it could also be a character encoded using ASCII, in which case it would be the letter B. It could also be part of a UTF-8 character string, or a floating point number, or part of some other data. So without any knowledge of the interpretation of this byte, we don't know what it means. We could have some JSON data about, I think about a person or something, which has an income of 100,000. Well, is this a lot? Isn't this? I don't know. I don't know what the units are. 100,000 euros per month is quite a lot. 100,000 Zimbabwean dollars in a year is not that much. So again, we need to know how to interpret this data. We could have a word, gift. If someone would give this to you and you speak English, you would be happy, you get a present. If you're a German-speaking person, in German, gift means poison. It all depends on how we use this data. I also have some other data for you. It's a prime number. It's not exactly a prime number because somewhere in the middle I replaced one digit with an x, and that has a reason. That's because if I would write down this whole prime number, it would be illegal in certain jurisdictions. And there's a story behind this. If you took this whole prime number, converted it to binary, put it in a file, it would actually be an executable file, and it would implement an algorithm to crack the encryption on DVDs. It's called DCSS. And well, that was forbidden, at least in America. So people started to find creative ways to encode that software in everyday things. Things that have to be published, like large prime numbers. There's a catalog online of the largest prime numbers ever found. This is one of them. So again, it all depends on how we interpret our data. To remember, data has a different meaning and are different interpretations. And data has no meaning by itself. We humans, or the code we write, gives it its meaning. So I'm a mathematician originally. I'm now a programmer. And one thing that mathematics and programming have in common is functions. And we will see what this has to do with interpretation and representation things. So let's look at what a function looks like. In high school, we might have learned something like this. A function is a kind of a box, a black box. We just put the letter F on it, and we put an X in, and we get a Y out. Simple as that. And well, the function is everything that happens inside the black box. But mathematicians are very interested in what kind of things this X and Y are. So mathematicians say, well, this function maps a certain set, a domain, D, to another set, its range, which we call R here, and it assigns for every member of the domain, so every X in the set D, it assigns a Y from the set R. And well, we could look at these sets as if they were classes in a programming language or something. And this may look very technical, but when we write PHP code, we often already do something like this, right? We have a function in PHP here, a function called f. And well, if we put an input type hint on it, it has one parameter, x, which comes from the set D, or in this case, it has a type D. And we put a return type on it, R, to indicate that its output, y, is always of type R. So actually, it's not that different. Let's look at an example. We could have a function that rounds numbers. Its input set, its domain, is a float, and it maps it to an integer, a whole number. And this function would assign to the value 3.84 the value 4. And in this case, it maps all the different floats to one other element in the set of integers. Now, it may happen that there are two different values, let's call them x1 and x2, in the set D, that this function maps to the same value y in the range. Something like this. If we put x1 in the function, we get back y. If we put x2 in the function, we also get back y. And we call such a function not injective. An injective function is a function for which this doesn't happen for any two values, x1 and x2. And you will see later what this means for our data. Let's look at an example again. We had a function that rounds numbers, and it maps both the value 4.35 and the value 3.84 to the same integer, namely 4. And value 4, it's sufficient to have 2. So this function is not injective. So if we could have two values in the domain set that map to the same range, could this also be reversed? Something like this. Could we have one x in the domain that maps to two different values in the range? Well, here it depends if you're a programmer or a mathematician. Mathematically speaking, this cannot happen. Mathematicians only use pure functions. So every input value, x, from the domain needs to map to one single value, y, from the range. But in programming, well, this is possible if we create an impure function. These are functions that do something with randomness, right? A random number generator or some function that uses a random number generator can have different outputs if we call it multiple times with the same inputs. Or functions that depend on some global input and output operations using the file system or a network. Or functions that are dependent on a system clock. You could have a function that asks for the current time, and every time you call it, you get back a different value. So in programming, this is possible. In mathematics, this wouldn't. Another thing that can happen is that there is a value x in our domain that we don't really know how to map to a value in set R. It doesn't really belong to the domain. Well, mathematicians have an easy solution for that. They just redefine the domain and say, well, this x is not part of the domain anymore. Very easy. Sorry? Yeah, it's an outlier. So they just cut it away from the domain and say, well, the domain is now all the values we had before, except for that x. It just doesn't go along. When programming, we cannot really do this often because, well, just think I cannot easily make a type hint that says, well, this can be any float except the number 0. There's no way to assign a type to that. So we often use another construct. Well, if we have that value as inputs, we just throw an exception, or maybe we return null. We just do something as a side effect to indicate that this is not possible. So what do this function have to do with data? Well, let's look at what I call representation and interpretation. And these are effects that functions have on data. So we have a round function again. And we can talk about the level of abstraction that this domain set and this range set have. If we are talking about the round function, which maps from a float to an integer, these two sets kind of live on the same level of abstraction. They're both numbers, we can do some calculations with them. They're not so different. But suppose we have a function that's called money, and it represents, well, a monetary value. And our function serialize money maps every one of those money values to a string that represents that money in a textual way. Now, it kind of lowers the level of abstraction by using this function, because our money is very rich. We can do all kinds of currency conversions with it. We can do mathematics with it, with our money value. And a string, well, we cannot really do something with it. Yeah, we can join them together or store them in a file or something, but we lose kind of knowledge by converting this money to a string. And we could have another function that kind of does the same, has the same effect. If we have a function that encodes a string as UTF-16, we even lower the level of abstraction even more. A string, we know what kind of characters those are. We can join them together. We can take substrings of it. And as bytes actually are, they could mean everything, anything. And yeah, we can send them over a network, but we don't really know what they mean anymore. So again, we lower the level of abstraction. And this is typical for something that we could call a representation. A representation is a function that translates a higher level concept to a lower level representation. Typical for such a function is that all the input values in the domain are supported, so we don't have this construct where we want to cut out one value, throw an exception or something. Well, we could represent any money as a string. Ideally, this function is lossless. We will see why a non-lossless representation is a bad idea later. And essentially, this function just returns the same data, but in a different form. So if we have these representations, we could also do the opposite. We can have functions that raise the level of abstraction. Next to our encode to UTF-16, we could have a decode from UTF-16, which converts an array of bytes back to a string, which raises the level of abstraction again. We could have a function that's called parse money, which converts string representation of a monetary value in our money object, which we can do all kinds of calculations and currency conversions with. Again, we raise the level of abstraction. And this is typical for an interpretation. It's a translation of a lower level concept, often back to a higher level concept that we usually had before. And typical for those functions is that they usually don't support all the input values in the domain set. So they throw some exception for certain values or return a null value. We cannot just parse any string into a money object. And not every sequence of bytes is a valid UTF-16 string. Right? So there are always values in the domain that we don't support. But again, if we support an input value, we return it actually kind of the same data, but just in a different form. So all this hassle, why do we even do this, right? We programmers, we like to work at a higher level of abstraction. We like to program in PHP instead of C or even assembly. And if PHP doesn't have a high enough level of abstraction, we use a framework to even raise the level of abstraction more, because a higher level of abstraction enables us to do more powerful stuff. Well, it's actually necessary sometimes to lower the level of abstraction, because if we want to store our data, this is how we store our data. These are just magnetic platters in a disk. And if you want to transmit our data over the internet, well, it needs to go through this. There's just electric currents or light pulses or something. And we cannot just put a money object through this wire. I've tried. So when we transmit data, what we have is we have data at a very high level of abstraction, and we need to transform it all the way down, 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 even further into bytes, and then we transform those bytes into light pulses or magnetic rains or whatever we use as a transport mechanism. And at the receiving end, or when we pull this data back from storage, we need to raise the level of abstraction back to work with this data. And we convert it, hopefully, to the same value we had before, if everything goes okay. So, I told you we were going to talk about escaping, and we will see what this has to do with this. Because a lot of people say, well, escaping of strings, that's something we do for security. What does this have to do with interpretation of data? So let's look at escaping for SQL, for HTML, for LDAP. Let's look at an example for SQL. Right. We have some script which accepts some data from a form or something, posted to that script, and it executes an SQL query on the database. So the user submits a username, and we select all the data from the users table in the database where the username matches the value we send. And here we put the db escape string function because we learned we should escape this input data coming from the user. Why do we do this? Well, suppose someone enters the string there on top as its username. It's kind of hacky. He just puts a part of an SQL statement as its username, and we put that in our SQL command. The database server executes it, and we have just executed the command to delete the entire users table. Right. So we learned to protect ourselves against these malicious users, we should escape the username before we put it in the SQL query. But is this really related to malicious data? We could have a user that's called John O'Shea or something, or, well, think of another Irish name with an accent. Query if we wouldn't escape it because of the quote in it. And it doesn't even have to be input that comes directly from the user. We could also have some code that gets a username from whatever API we use. It's not directly submitted by the user, but again, if this function for some reason returns a string John O'Shea, it would break our query if we didn't escape it. So what this is just this data. It's not malicious or something, and it doesn't matter from what source it comes. It's just we have data, and we need to represent it in the correct way to put it into an SQL query. So what I want to stress is that string escaping is not a security measure. It is necessary for security, but we don't do it because of security. And trusting data is not a reason to omit escaping. String escaping is something we do just to properly represent the data for the use case we're having. So we could look at escaping as a representation. We could have a function that's called dbEscapeString, which translates a string into something. It's quite awkwardly named. I just named it SQL fragment because it is a strange thing. It's something that we can put into an SQL query, but it's not a complete thing because, well, it misses the quotes to be really a string representation in SQL. And this is where part of the confusion comes from. Our escape functions typically look something like this. We put something in, and it escapes all the characters that are inside it. But it would be better and more useful if we had escaping functions that look something like this. Something that is named like it represents something as something else. It represents a string as an SQL string literal, and then returns the complete representation of that string in SQL with the quotes on both ends. So that would be a complete string, and we could name that an SQL string literal. It would look something like this. Again, it maps something as a string, and it dumps it down to an SQL string literal, which we can send to an SQL query, but we don't know the original string anymore. And if we view it like this, we could also easily solve problems with nested escaping if we think of them as representations. Suppose we have a use case where we need to put a name, which can again be John O'Shea or something, in JavaScript, put that into an HTML attribute, and then store that HTML fragment in a database. We need to escape 3 times, or actually, we need to represent that data in different forms, nested. First, we convert it to a JavaScript string literal. Then, when we put it into an HTML attribute, we need to represent that JavaScript part as an HTML attribute. And then again, if we put that HTML snippet into the database, we need to represent that string as an SQL string literal, which we can put in our query. And what often goes wrong here is that people do stuff like this. At the beginning of a script, they go over all the user input to that script, and they already escape the data. Because, well, the data can be malicious, and if we escape it, the data is now safe. So what we do here is we escape the data for usage in a database and then put HTML escaping over it. And that assumes that we are going to put that data in a database and then use that same data to put in an HTML page. But we don't even know what we are going to do with this data at this stage. At the beginning of the script, we could do anything with this. We could send it over the network to something else. It doesn't even have to enter an SQL database. And this is where you get all the extra quotes in that you didn't intend. So don't do stuff like this. Only represent data for the use case that you're having at the moment that you are translating it, right? If you are going to put data in an SQL database, represent it correctly for SQL at the moment you're executing the SQL query, not earlier, because, well, then we're just guessing what we are going to use the data for. And another pattern that happens a lot is something like this. Also, at the beginning of a script, we go over all the user input to that script, and we try to see if there's some malicious data in it, like, well, a drop table fragment that we had earlier. But we don't even know if this data is going to go into an SQL statement. It might be that I want to upload my slides, which contain the string drop table, or that I'm writing a blog post about SQL injection or something. With a system like this, which directly exits if it sees the string drop table, I cannot do that, right? So again, there's no need to fear for these strings. Those strings are not evil. It's just we need to properly represent the data for the use case we're having. So we already saw one situation that goes wrong. Let's look at some others. If we have a money type again, and we have a function to serialize that to a string, right? We could do that like this. I use the thing between the braces to just signify the abstract thing that is a money instance that represents 10 euros. And we could serialize that to the string 10 euros. That's fine. But we could also have a function that serializes that money like this. It maps the string 10 euros just to or the money object 10 euros to the string 10. Well, what's the problem here? Well, in our set of all the money objects, there's also another value that's called $10. And if we would use the same representation function to represent the $10 as a string, it would map to the same string 10. This function is not injective. And what happens then is if we transmit that string and we dumb it down further and submit it as magnetic grains or light pulses or something over a wire or on a disk, and then we want to raise the level of abstraction again, well, we have the string 10 and we want to parse it as a money object. So what should it be now? Right? We lose knowledge because we incorrectly represent the data. Our representation is not lossless. And of course, this is a contrived example, and you're saying, that doesn't happen to me. I don't do this. It's so dumb. But well, don't we do this? We have a date time somewhere in the future, in 2022. Maybe I have an appointment at that moment. And we even have a time zone with it, Europe, Amsterdam. And we want to represent that date time as a string. And we could do that like this. Well, looks okay. It even has the time zone, the +1 with it. But right now, people are talking about abolishing daylight saving time, maybe switching time zones. I don't know if in 2022, Europe Amsterdam will still be +1. We might be at +2 at the moment, +0, I don't know. So by converting the date time at the top and representing it as a string below, we're losing the knowledge that this +1 is meant to signify the time zone we're living in, Europe Amsterdam. Again, we're throwing away data. We could have a fraction, 1/3, and we could represent it as a float, which has only a limited number of decimals. It's kind of a contrived example, but again, if we have the value at the bottom, we don't know whether that was exactly 1/3. It could be 33,333, etc., of a millionth of something, right? So again, if we store this data incorrectly, we throw away data. We could have a string which is full of all kinds of characters and emoji or something, and you might try to encode that as ISO 88591, which is often used as a string encoding. But that doesn't support all the emoji. I don't even know what it will produce. Again, we're throwing away data because not all our emoji can be represented using this encoding. So to keep in mind, if we use the lossy representation, it cannot be faithfully reinterpreted again, and we lose data. So if we talk in terms of the function theory, make sure your representations are injective. That ensures they can be inverted and interpreted back to the value we originally had. What can also happen is misinterpretation. So we have already some representation of our data and we want to reinterpret it to a higher level of abstraction. Suppose we have some byte sequence that we can decode from UTF-8 to obtain a string, something like café. So this maps from the set of byte sequences to the set of strings. But not all byte sequences are a valid UTF-8. They're actually a subset of that. Right? So there's the darker set, which represents all the values that we can interpret using decode from UTF-8. And the light blue set are those that we cannot decode in this way, which throws an exception. But there's a problem, because within the same set of all the byte sequences, there are also the byte sequences that we can interpret without an exception as ISO 88591. And those sets partially overlap. So we could try to decode that same byte sequence using the other string encoding. And if we do that, we get the string that you probably sometimes see in your browser if someone messes this up. At least it's copyrighted, but it's not what we originally intended. Right. So the problem is the situation we have here. We have those two sets and they overlap. And if we have a value in the overlap between the two, we don't know if it was intended to be the one or the other. But luckily for this problem, PHP has a solution for us, at least it says. there's a function mbDetectEncoding, which detects the character encoding of a string. Wow, how can we do that? This string is both valid as UTF-8 and as ISO 88591. If we don't know how it's meant to be interpreted, PHP cannot tell this for us. mbDetectEncoding actually just tries a number of character encodings in sequence and just returns the first one that produces a valid answer. But it can be the wrong one. So remember, the meaning of data always comes from our own interpretation of it. And our own interpretation of that may be very well wrong. Or well, wrong, at least not how we intended it. So what can we do to solve this problem? We could use something that I like to call interpretation hints. We can store or transmit something along with our data that signifies how it should be interpreted to avoid us messing it up. And there are a lot of examples of this in the wild. Things like HTTP headers. When we get a HTTP response, it includes a content type header, a content encoding header, and maybe even a content language header. And it tells our browser how it should interpret the response we just sent. It says, hey, this is an HTML page, and it's encoded using UTF-8. And if you decode it like that, it is in Dutch. So your browser knows how to display it, right? If we wouldn't, our browser had to guess how to interpret the data, and it would probably mess up. And there's something called the UTF-8 byte order mark, which we include in character strings to indicate if they are big endian or little endian. I'll show this later. But it's also outside programming, we also have examples of this. For example, if you have sheet music, it's always 5 bars and some notes on it. And without the key at the beginning, we wouldn't know how to interpret these notes, right? If we have the same notes but a different symbol in front, they would translate to other notes to play. So also this is a hint for how we should interpret this data transmitted with the data itself. So what does this look like in case of the byte order mark? Well, we have the set of all the byte sequences that are valid UTF-16 little endian with a little byte at the end. And we have the set of all the byte sequences that are valid UTF-16 big endian with a big byte at the end. And again, they overlap, so there are values in the overlapping part of this set that are valid as both. And if we would interpret that, we wouldn't know how to interpret that. But if we include a byte order mark, these sets are different because all the values in the left set have one byte order mark and all the values in the right set have another byte order mark. So we cannot mix these anymore, and if we have a value, we can see from the byte order mark how we should interpret it. So we have 2 overlapping sets and we just pull them apart so that they're non-overlapping anymore. And if we have a value, we know which set it belongs to and which set it doesn't, and we know how to interpret that. If transmitting the desired interpretation along with data is not possible, we could also opt for something else. We could include some hints in our variable naming. We could call something message UTF-8 to indicate that it's UTF-8 encoding. We can call something username SQL to indicate that it's already represented as an SQL string. We can call something title HTML to indicate it has been represented for inclusion in HTML. And using such a convention allows us to spot some errors, like this. Here we output headers that something we are going to send should be ISO 88591. But directly below that, we output UTF-8 data, which we know is wrong. Or if we have something like this, we execute an SQL query and we put into that a variable that doesn't have the SQL suffix. We know this data is not properly represented for usage in SQL if we stick to this convention strictly. Or we could have something like this. We put something in HTML entities which we know is already valid HTML. So we're double encoding this entity. Right? These are all things you can do to make this problem, well, a lot less common. So what makes this even more difficult Well, we were talking about all the byte sequences and string stuff. And then we go work with PHP, and things are just a little different. Because, well, we'll see. If we have a function encoded as UTF-16, we said that this function maps strings to byte streams, sequences of bytes. And that's it. That is how we would look at it from a pure way, right? A string is just a sequence of characters, might be all kinds of emoji and things like that, and we know how to take the end character of that, and we can join strings together and stuff like that. And bytes are just dumb bytes for transmission. But in PHP, this is not really how it is, because PHP string type is actually a byte array. PHP doesn't know anything about real strings and what is a character. PHP just stores strings of bytes, actually. So every time we use the string type in PHP, it's actually just an array of bytes without any knowledge about that. So what our encode as UTF-16 function actually looks like, it's more something like this. It maps from the set string to the set of byte arrays, which is actually just the same as string. So it maps from a set onto itself. And this means that we don't get the higher level of abstraction to work with. And instead, what we have to do is, well, we don't interpret this data once to a higher level of abstraction, but every time we use this data, we just use it, we just reinterpret it every time. It's almost as if we put on a certain set of glasses to look at that data, and then we need to put other glasses on at another time. So every time we use this data, we need to reinterpret it because we cannot raise the level of abstraction once and for all. And this also leaves room for misinterpretation, because we could also use that same string byte sequence as if it was UTF-8. And then we would get another string, which was probably not what we intended, or it was. We don't know. So to solve this problem, we need some more accurate types. And well, since PHP doesn't provide them to us, we could make them ourselves. So let's look at a solution using value objects. And this is kind of fancy, it's kind of comprehensive, but well, there might be solutions where this is useful. So we could implement a class, which we call UTF-8 bytes, to signify byte sequences that are valid UTF-8. And it has a constructor which accepts, well, bytes in the form of a string because we need to put a valid PHP value in it. But we make the constructor private, and we only use static constructors to create it. So we have explicitly from what we convert it or to what we convert it. And to make the slides a bit shorter, I use PHP 7.4 type properties. In PHP 7.4, this syntax will become available, and you can assign types to your properties, which is really nice. In the same way, we could create a class which is called ISO 88591 bytes, which represents byte sequences that are valid according to ISO 88591. And it looks kind of the same, except for the name, and this is how we keep those two sets separate. And what we can now also do is create a value type for our real string, a string that actually raises the level of abstraction. So what we do here is internally we represent all the strings as UTF-16. That is also how, for example, a language like JavaScript does it. But we make our constructor private again, and we use static constructors, for example, a constructor from UTF-8. And by doing that, we hide all the knowledge about the internal encoding being UTF-16 inside the class. So from the outside, we don't know what the internal encoding is. We just say, I want to create such a real string from a UTF-8 byte sequence, or I want to create such a string from an ISO 88591 sequence. This is all type safe, so we cannot mess this up. And then we have a real string to work with. So what can we do with it? Well, we can represent it back as a byte sequence to UTF-8 or to ISO 88591. And again, it uses the knowledge that the internal encoding is UTF-16, it converts it and returns the correct value type. And what we can also do, which is what we actually want to, well, make use of our higher level of abstraction, we can do string operations, things that we really wanted to do on a string and which we don't want to know the encoding for. We could concatenate strings, which is now, we know that they are both in UTF-16 internally, so this function can just join two such strings together. We could take a substring of those strings without worrying about the encoding they were originally in. So how can we use this? Well, we could have a file1.txt that we know to be in UTF-8. We can read the bytes from that string and convert it to our real string, which has a higher level of abstraction. We could have a file2, which we know to be encoded using ISO 88591. We can read those bytes, convert them into a real string, and now we have two strings at a higher level of abstraction. And the original character sets those files were in don't matter anymore now. We can just do all kinds of string operations, concatenate these strings, take a substring of them, without worrying about any encoding issues here. And at the end, we can represent them back to a byte sequence, dump that down to a PHP string, which is actually just a byte sequence, and output it. So only at the boundaries, at the input and output stages, we work with PHP string type and the byte types. And internally, we can all work with, well, a higher level string abstraction. So again, what this looks like is, well, without the value objects, we have the sets of the UTF-8 sequences, the ISO 88591 sequences, and the string type, which is actually just the set of byte sequences which encompasses them all. And with the value objects, we separate those sets and create a new set which contains all the real strings at a higher level of abstraction. We just interpret the data once, and we can then work at our higher level of abstraction. So our value objects have some advantages for this situation, but we should also remember that this is not a silver bullet, right? It comes with considerable overhead. We need to convert the internal encodings to UTF-16, which is quite an operation, and it's quite a lot of code to write, and well, your syntax becomes a lot more involved. So you shouldn't use this for everything. But if there are pieces of code which are, well, heavy on character encoding and easy to mess up, you might use a strategy like this to make it easier on yourself and prevent yourself from making mistakes. So what have we seen today? We have looked at data, the nature of data, and how the meaning from data is derived. We have looked at functions, how does function operate on data, how we can see these functions as interpretations and representations of this data, why that is necessary evil for transmission or storage of the data. We have looked at string escaping, which is actually just a way of representing your data, not necessarily a security measure. We have looked at misrepresentation and interpretation of our data, how the string type makes it even more difficult to get right, but how value objects might in some situations be a good solution to help yourself get it right. The most important thing to remember is this. The meaning of data is always defined by how we interpret it. Data has no inherent meaning. We assign a meaning, and we can do that right or we can do that wrong. Thank you. So are there any questions?
In one of the first slides, you were talking about storing a currency number as, for example, €10 as just the number 10.
Yeah.
Would you be okay if you store the number 10, but you also write in another?
Yeah, that would be fine, because in that case, the two pieces, the number 10 and the currency, would together form the corresponding piece of data. So that would be fine. In essence, it would represent the money object not as just the string 10, but as the pair of, well, the string 10 and the string euros. And that's a nice representation of that data.
All right, but in your code, you would always have to refer to both those numbers.
Yeah, but then you should treat them as a pair. It's just a pair of those two values, and you represent it, well, from the money object to the pair, and you interpret it again from the pair of those two values to the money object. If you would separate those two parts from that pair and, well, treat them differently, then you would be in a danger zone, I guess. Any other questions? All right. Well, if you have any more questions, I'll be around. Feel free to talk to me and ask more. Thank you.
Ask more.
Thank you.
Thank you very much for your very interesting talk. Well, I would like to invite you all now for driving a lap in our phpCE and for beer, of course. But I would also like to mention the next Ode to the Code is about immutability. Also a mighty interesting subject, which will be in less than a month on May 23rd, if I remember correctly. It's on Meetup, so I would like to invite you all to join us there. And now let's have a beer and talk to Arnout if you want to. Thank you. Dankjewel. Graag gedaan.